All right, this is page 4 of notes 1 of math analysis. And what we're doing is, I guess it's actually just page 4 of math analysis because math analysis goes straight through to page 329. I just realized that. What we're going to do now is talk a little bit more about arc length while we're like on the topic. It's really important. I mean, you end up using arc length in a lot of places. Like later, you get to Calc 2 basically is where arc length comes back in sort of a big way. But let's think what we can do here. So write a formula for finding arc length if the central angle is measured in degrees and another if it is measured in radians. All right, so arc length given degrees. So if I'm going to say if x is in degrees, so I'm going to use x as my variable because I can actually use anything. Like usually you're going to see theta and phi. Those are the most, and alpha, beta, gamma, a lot of Greek letters, honestly. X and Y are perfectly good. We could use those for angle measures. So if X is in degrees, then the arc length S is going to be, what are we doing? We're doing a ratio, right? So you got your whole circumference, but you only have part of it. You have X out of 360 degrees of it, which means that you have, so I'm going to do an arrow there. S is pi over 180 degrees, and then r times x, which is also in degrees. So I'll put a little degree symbol. You don't really need to do it because it said x is in degrees, but so look at that formula right there. It's kind of interesting. Like you can rewrite this or rearrange it a little bit and say that you have s is pi over 180 times x and then times r. What's pi over 180 times x? That's just taking x in degrees and converting it to radians. This is crazy. This is something, when I first learned this, I felt like I had been cheated in geometry. I felt like every formula that I was learning in geometry had this like random pi over 180 in it. Like it shows up a lot of places. Go back to your geometry notes and take a look. And every time that pi over 180 is there, you're literally just kind of like shadowy converting to radians to make it work. All of geometry wanted to be in radians. We just didn't really realize it at the time. And isn't that weird? Like I felt a little cheated. So if I'm going to do this, let's say that let theta be in radians, I guess. Well, this one, I actually know something that can help me immediately. I know that theta in radians is S over R. And if that's the case, then it must just be the case that S is R times theta. This is a formula. You can use this all the time, and you will use it all the time. I actually have it memorized more this way, S equals R theta, than I do that theta is equal to S over R. Like I have to do this tiny little calculation in my head every time because I memorized S equals R theta. I don't really know why I chose to do that. We also could have gotten it straight from here. We could have looked at this and said this is just theta in radians. So that'll give us S equals R theta. Either way, we're getting the same thing. So you can see that S equals R theta, it's just so much simpler because we don't have to take out the arbitrary angle measures that we were using. That's what that pi over 180 is doing. It's converting from arbitrary human degrees into how many radians are in a circle. If we thought there were 400 degrees in a circle, that would have been pi over 200, and we just would have kept going. Why is it pi over 200? Because there's 2 pi radians in a circle, and we're claiming there's 400 degrees. 2 pi divided by 400 is pi over 200, and you just kind of go from there. That's going to be important in a couple pages when I start making up angle measures, by the way. That notion of doing a proportion of how many you think are in a circle to how many radians are actually in a circle. But let's not get there yet. So S equals R theta, it's a formula. You can solve it any which way you want. Solve for R. R is equal to S over theta. No one ever uses that, but it's a thing. Theta equals S over R, S equals R theta. Any of them are valid. So let's see if we can do this. Find the measure of a central angle of a circle, radius 8. So R is equal to 8. And the arc is 72. 72. Okay, so then I know that theta is S over R, so it's 72 over 8. So it's 9. 9 radians. Pause and think about that. 9 radians. So 2 pi in a circle is 2 times like about 3.14-ish. I only have it memorized as 2 decimals. Sorry, all you people who memorize pi. So it's about 6.28 in decimal form. This is bigger than a circle. What is happening when you get an angle that is bigger than a circle? Well, one thing to think about is you want to start thinking of your angles not so much as something you take a protractor and put down to measure, but think of them more as how much did something rotate, right? So like, say you're sitting on a chair that rotates, like I am right now, right? How many radians am I rotating? Well, if I rotate all the way around and then more, I'm going above 2 pi radians. That's what's happening here. It's as if we're starting, let's draw a circle. Right, so if we start, if we start here and we go all the way around, this would be 2 pi, which is 6.28. But then I need to go like a little less than 3 more. So probably I would end up maybe here-ish, totally making that up, which would be a little bit more, right? So if, let me erase this. If I started here and I rotate, that'll be 6.28 and then more. This angle that I've rotated could be theta equals 9. I just went more than one full rotation. That's actually totally fine. I mean, think of the wheels on a car. They just spin and spin and spin and spin, right? And if you're hearing like a weird knocking noise every like 5 spins of the tire, you want to be able to talk about that, right? That's every 10 pi that the tire rotates through. You're hearing this weird knocking sound, or maybe it's the engine or whatever it is. You need to be able to measure these sorts of things. So angles can go way over 2 pi. They can actually be any real number. They can go negative. What? That just means you're going in the opposite direction. So typically we're going to rotate counterclockwise and call it positive, which means clockwise is negative, which is a little confusing because you feel like maybe clock should have been the standard, but they're not. All right. Find the length of an arc intersected by a central angle of measure. So theta is 3 pi over 8 in a circle having a radius. Okay, so you want to be think in radians as much as possible. Always radians. Can't stress that enough. The sooner you develop that as your like go-to, the better off you'll be. So this, okay, we know r and theta, so I'm just going to say s equals r theta. So s is going to be r, which is 24, times theta, which is 3 pi over 8. You know, I want to go back and do something so that I can yell at you about something. You know, in order to do that, I need to, you know, be better. 9 pi. There are no units, so I'm just going to say that that's my answer. So s is equal to 9 pi. Oh, I got to like make my, I know what's happening here. I got to make my highlighter bigger. There we go. Okay, so I want to go back here and I want to change this so that I'm actually showing the formula that I use. Poor form on my part. You should always show the formula that you're going to use. So we're thinking theta is s over r. Once we say that, now we can substitute in and someone can read our work and make sense of it, which is the whole point of doing any of this. There's no point in just you doing your work for you. It's all about like communicating math, sharing it, but you got to know what you're doing. So here we get this. And then let's look at this. Find the radius of a circle. If the central angle would measure 36 degrees, no, we're not using degrees. Let's convert that immediately. So 36 degrees, I'm not even going to finish reading the problem. 36 degrees pi over 180. So I know 180 is 5 times 36. So this is just pi over 5. Okay, our angle theta in radians is pi over 5. You should only be working in radians. Intercept, so this is this we said was pi over 5 radians. Intercepts an arc of length 64 pi, so that's s is 64 pi. And we've said theta is pi over 5. And then find the radius. So I'm going to say I'm actually just going to say S equals R theta, and then therefore R equals S over theta. You want to like manipulate it with the variables instead of the values because it's just easier. And so this means that R is going to be 64 pi divided by pi over 5. So why would I put 5 over pi? Pi over 5, which means, maybe I'll just go down another level. R is 320. There are no units on these problems, which is sort of maddening. But, you know, no units, no units. So 320 things, I guess, is what we're getting. Big circle, huge circle. Pi over 5, 36 degrees, like not that big an angle. So to get an arc length of 64 pi, you needed a big circle. So you kind of start to get this like sort of like radian sense, right? Like it's kind of like number sense, but a little bit different. Pi over 5, not that big, right? It's think of pi, it's 180. You're going to divide that by 5. You're going to get 36. So I literally just converted it back to degrees to like make sense of it. And you kind of just do that. I mean, actually, like much to my chagrin, I only speak one language. I wish I spoke more. But like I always imagine that's probably what people do. Like even when I was trying to learn another language, I was constantly like having to re-reference back to like what I was familiar with. You're familiar with degrees. You're going to try to use degrees all the time. Life gets easier when you turn into a radian speaker, right? That's what we want to do. But anyway, these problems are just a couple of arc length things. Just want to make sure that we hit those. S equals R theta, theta equals S over R. Those are the big deal things. And then you can just use it as a formula. So if you know 2, you can find the third. And you end up with basically some like pretty easy algebra 1 level questions, I would say. Anyway, I'm going to stop this here, come back in the next video, and keep going. So I will see you there.